an SVC application example in Scikit-Learn. So here we will work again with the iris dataset that you are already familiar with. But we want to perform two-class classification, by-class classification. And if you remember, the iris dataset has 3 classes. So we will have to modify the data to basically single out one of the classes and only consider 2 of the classes. Also for visualization, we will have to use only 2 features because we have 4 features in the iris dataset. So for visualization, we need to only pick 2 of the features. Also, the iris dataset is a standard dataset already available in datasets module in Scikit-Learn. But here I want to show you how to work on it and access to it in a different way. So basically, we're going to access the dataset from a repository on the University of California Irvine website. So this is going to be a different way to do that. Of course, it's going to take more time and more coding, but I want to make it flexible for you that no matter where your data is, you can actually access that. So please download the IPython files and open the template file and follow along. Happy coding. By importing the libraries that we need pandas and matplotlib pyplot. The data that we work on is the iris dataset, which you can have it. You have it actually the URL address, which is stored in the University of California website. And we're going to read the data using these variable names that is stored in column names. So we have sepal length, sepal width, petal length, and petal width. And the last one is the class or the label. So we have 4 feature variables and we have the class or label. So let's read the data using the pandas read CSV. I'm going to read the data and put it in iris underscore data. So I'm going to give the address, the URL address, and then I'm going to ask read CSV command to read the data within these names, the column names that we specify here. All right, and let's now take a look at our data that we have read just using the head. So this is our data that we have the first 5 samples of data. We have 4 features here, and we have the classes, the label, the last one, which we have 3 classes here. We have the iris setosa and virginica and versicolor. So what we need to do, because we want to do a by-class classification, we have to get rid of one of the classes, and also for illustration we want to have only 2 dimensions, so we need to keep 2 of the feature variables and get rid of the 2 other feature variables. So we need to modify our data. So before we do that, let's actually take a look at the shape of the data that we have here. So we have 150 sample, which means data points, and 5 columns. 4 of them are the feature variables and one of them is the label. So out of these 4 feature variables that we have, and also the 3 classes that we have, because we want to do a 2-class classification and a by-class classification, we need to modify our data and keep 2 of the classes and get rid of the other class. And also for illustration purposes, because we want to have only 2 dimensions, so we need to keep 2 of the features and forget about the other 2 features for illustration. So what we're going to do, we're going to modify our data for these purposes. First, we're going to single out the third class, which is the iris versicolor, to make a two-class data set. So let's do that. All right, so our new data, I'm going to call it data set, and that's a copy of our iris data set. Only the two classes that we need, and we're going to single out the iris virginica. So copy everything except the iris data class. So what this does is going to go to our data, which is iris data set, and for every data points that the class, its class is not iris virginica, it's going to copy it. So that means that this is going to single out, copy everything except iris virginica. Also, for illustration, we need to keep two features and get rid of the other two features. So we're going to drop the sepal width and petal width from our data set. So we need to do another modification. Now our data is data set because we copied everything except iris virginica to data sets, and we want to now get rid of these sepal widths and petal widths. So we're going to keep working with data set from now on. Okay, so we're going to drop two of the features, so two of the columns. So we're going to use the drop function, and then the name of the one that we want to drop. So that's sepal width. I can copy it here. And the other one is petal width. All right. And x is equal to what? We want to drop the columns. All right. So now let's take a look at the shape of our data. See what happened. So we used to have 150 sample of data. 50 of them, that means a third of them were iris virginica, which we got rid of. So now we don't have that. Also, we used to have 5 variables, 4 features and 1 class variable. Now we got rid of the sepal width and petal width as 2 feature variables. So now we have only 3, which is going to be the sepal length and the petal sepal width and class. All right, so let's now go for plotting. We want to plot our data. Now we have 2 classes and 2 feature variables, so we can plot our data. So what we're going to do, we're going to define Setosa class and versicolor classes. So we're going to specify the class equal to the iris Setosa, because this is for Setosa, and we're going to do the same for versicolor class. Right. So also let's do that for the other class, which is versicolor. All right. And we want to define the sepal length as x variable and petal length as y variable, because we only have these 2 feature variables. So one of them is going to be our x and the other one is going to be y. So we can actually plot the data. setosa x, that's all of the setosa class that we have, only the sepal length. And for the setosa xy variable, that's going to be setosa class and the petal length. All right. So we need to do also the same for the versicolor. We need to define versicolor x and y. Versicolor x, that's the versicolor class, the sepal length. So I'm going to copy this part here. And versicolor y is versicolor class petal length. All right, now let's take a look at the two classes that we have here. PLT figure, we want to specify the fixed size here. For example, 8 and 6. And then we want to also specify the type and color of marker. So, and we want to have a scatter plot. So it's plot PLT is scatter, and the x value would be the setosa x, and setosa y. These are x and y variables, and we want our marker to be, for setosa, we want our marker to be, for example, a star, and the color of that star we want to be red, for example. And we're going to specify this also for the versicolor class. So this is versicolor. And the marker we want it to be a small circle, and color we want it to be blue, for example, for distinction. All right. So let's now see the algorithm, the plot. Yeah, as you see here, we have two feature variable. The x's are the sepal length and y variable is the petal length. And we have these two classes. The stars are the setosa class and the blue are the versicolor class. So just by illustration, you can see that what we want to do using a support vector algorithm, we want to have a hyperplane, which is a line here, to distinguish and separate and segregate these two classes from each other, which looks like it's not a difficult task to do. I want to implement the SVM algorithm. So let's go ahead and do that. The first step is we need to define x and y variable. So our x variable, I'm going to show it by capital X because we have two feature variables, and that's going to be our data set sepal length and petal length. So sepal length and petal length. And the y variable is just going to be the class. So data set class. C is capital here. All right, so now we have our feature variable X and dependent variable or label variable Y. The next step is to split our data into training and test. So first we need to import the split. And then we're going to give it the X and Y. And also the test size, for example, we can specify to be 20%. That means that we're going to have 80% for training and 20% for testing. And the random state, we're going to also set it up so we would all get the same output. So I'm going to initiate it with 0. All right, so now we have our training data and test data. So let's now go ahead and develop our model. So first we need to import the model from Scikit-Learn SVM module, support vector machines module, import a classifier for support vector machine, which is SVC, support vector classifier. Okay, and then I'm going to make a copy of my SVC, and that's a copy of SVC, and we can specify the parameter that we need. So right now we're going to only specify the kernel function. So I'm going to specify the kernel function as linear, because a linear line would work here. And next we need to train our algorithm using the training data set. So that would be dataset class sepal length. All right. So our algorithm is trained and we are ready to make a prediction. Prediction on the test data set. I'm going to call it yPredict. Then I'm going to ask my SVC algorithm to make a prediction on the test data. And we're going to do the same for the training dataset. All right, so let's now see the accuracy score for our prediction. So first we need to import the accuracy metrics. So from Scikit-Learn metrics, import accuracy score. All right, and here we're going to make our prediction. SVC accuracy on test data is equal to, and then I'm going to give it the accuracy score. And we're going to do the same for the training dataset. So I'm going to copy this here on test training data. Okay. It looks like that it worked great. We have 100% accuracy because we actually split the data. We got rid of 2 of the features. We also got rid of 1 of the classes. So here it's a standard data set, so that's why we have 100% accuracy here. but no, that's not something that we usually get. We get not even close. SVM classes. There are different SVM classes. We have SVM classes for classification, such as SVC, which is support vector for classification, or support vector classifier. We have no SVC, and we have linear SVC. These are SVM classes capable of multi-class classification. For regression classes, we have SVR, which is support vector regressor, and new SVR. For classification, the new SVC is similar to SVC, but uses a parameter to control the number of support vectors. Nu is an upper bound on the fraction of training errors and a lower bound on the fraction of support vectors. SVC and nu SVC versus linear SVC. What's the difference? SVC and nu SVC are similar methods, but accept different set of parameters and have different mathematical formulations. Both SVC and nu SVC implement the one against one approach for multi-class classification, which if we have n classes, that would be a total of a combination of 2 out of n, which is equal to n multiplied by n minus 1 divided by 2. On the other hand, linear SVC implements a one against the rest approach, which is a total of n if we have n classes. Multi-class classification using different SVM models. Here you see an example from the Scikit-Learn documentation library. You can access that online. So here we are working with the iris dataset, the same dataset that we have 3 different classes, and we have 4 feature variables, but because we want to visualize it here, as you see here in 2-dimensional, we only have the sepal length and the sepal width. So we ignore the petal length and petal width for illustration purposes only. And here we have 4 different models. We have the SVC with linear kernel. We have linear SVC, which has linear kernel. And we have the SVC with RBF kernel and SVC with polynomial 3-degree kernel here. So as you can see here, for the SVC with linear kernel and also linear SVC that we have here, both of these, if you look at this classification, these boundaries or the hyperplane, which are lines here, I mean, they are a split hyperplane, if you imagine that, then you see that these are linear, right? These are straightforward linear. And for the SVC with RBF kernel, you see that these are not linear. These are non-linear boundaries. And same is true for the SVC with polynomial. As you see here, this is also non-linear. So let's see the codes. Another project is another piece of code that uses and apply different classes of SVC and SVM, the support vector machine. It applies the SVC classifier, it applies the new SVC and linear SVC. You have access to these codes, but you're not going to actually develop these codes from beginning. It's a little bit more advanced. So I'm just going to go sketch through it, and feel free to go through it on your own time. So here we just import the libraries that we need. This function make mesh grid is just going to create a space for us to plot the data that we have. Actually, we are going to work with iris data here. So here it's going to plot all the data, different classes that we have of plants, flowers, and also it's going to also plot the hyperplanes here. So make mesh grid, this function is just going to create a canvas like that you can plot on it. Okay. The next one is plot the plot contours. So this is going to just plot the hyperplanes for us, and also make colorful environment for it. So here we import the iris dataset from load iris, the datasets that we have actually, it's one of the dataset that is available in Scikit-Learn. And we only need to have two features here because we want to plot it, so we want to have two-dimensional. So that's what we do here. We split our data into X and Y. Then here we make our models. So C is a regularization parameter, and we create the models, and this is what we use. We use the SVC, the linear SVC, and the SVC with different kernel here. The RBF kernel, linear here, the poly kernel as well. Also, we set different parameters for gamma as well, and the degree as for the poly, of course. So here we have actually created 1, 2, 3, 4 different models. And then in this same line, as you see here, this is how compact, this is like the power of Python, how compact is it. And this line, this one single line, we actually fit or train our models, 4 models at the same line. And this is with just title of our plot, and we're just going to plot it, make actually classification using these 4 models, ask our models to make a classification on our data, and then plot the output including the contours, or actually the hyperplane, as you see. The kernel functions that are available in Scikit-Learn that you can apply to your support vector machine algorithm are including the linear function, polynomial function of every degree, the radial basis RBF, and the sigmoid function. Also, you can actually develop your own custom functions. So this is how flexible and powerful Scikit-Learn is. For example, this is a piece of code that you can write, and then you can write your code for actually your own function here. And then you can use that as a kernel function. Let's now see the advantages and disadvantages of the support vector machines algorithms, starting with the advantages of the algorithm. The SVM algorithms are effective in high-dimensional spaces. That means that if you have a lot of features, this is going to be probably a good choice. It is still effective in cases where the number of dimensions is greater than the number of samples in your training data. So even if the number of dimensions that you have, the number of features is even more than, that means the number of columns in your data even is greater than the number of rows. The number of rows is just the data points or samples of the data that you have. And the number of columns are just different features or different variables. So even if your dimension or the number of features is greater than the number of data points or samples that you have, this method can still be effective. SVM algorithms are memory efficient. It means that it uses only a subset of training points, aka the support vectors. So that's why it makes it memory efficient. It doesn't have to work with all the training data. So what it does, as we have figured out, it's going to find the decision boundary or the hyperplane, and that's it. Based on that hyperplane, now it can use to make a classification and prediction. Now let's see the disadvantages of SVM algorithms. Efficiency, runtime, and memory decreases as the size of the training data increases, which is a problem with most of algorithms. Normalization and parameter tuning are required. If the number of features or number of dimensions or number of independent variables or columns is much greater than the number of samples, there is a risk of overfitting. Choosing right kernel functions and regularization is a must in that scenario. Tips on practical use of SVMs. Setting the parameter c, which is the regularization parameter. The default value for c is 1, which is a reasonable default choice. If you have a lot of noisy observation, you should decrease c. What it means is if you have a training data set that has a high variance, it varies a lot, to avoid overfitting your model into your training data set, you need to have more regularization. More regularization for SVC means higher value for C, the regularization parameter. So if you want to have more regularization, decrease C. If you want to have less regularization, increase C. It is highly recommended to scale your data. So normalize your data when you want to use SVM. In support vector classification, SVC, if your data is unbalanced, meaning that you have more data points or data samples from one class than you have from the other classes. So this is what it means to have unbalanced data. You can set the class underscore weight, this parameter, to balanced, and then try different C values. Let's see more tips on practical use of SVMs. If you have unbalanced problems, that means that you have problem that you want to put more emphasis on certain classes in your data, or certain data points or samples in your data are more special or more important. What should you do? Well, SVC actually has an option for you. In problems that is more desired to give more importance or emphasis to certain classes, you can do that by using the class underscore weight, which is only available in SVC, during the training or feeding process to do that. So this parameter lets you to assign different weights on different classes. On the other hand, if you have problems that certain samples of data or data points in your data are more important, or you want to let them have more say or influence on your model development, then you can do that by using the sample underscore weight parameter. This would let you to assign different weights on your samples data. That means rows in your data. For a list of other parameters, you can see the Scikit-Learn's documentation, which is available for free online.